Alright, so electronegativity is a very important concept that will help us determine whether electrons are going to be donated or accepted, or whether electrons are going to be shared between two different atoms. And so we can see that the periodic table actually holds trends for this concept of electronegativity. So the first thing we need to do is really define what electronegativity is. Electronegativity is the ability of atoms in a molecule to attract electrons to itself. So if we look at the periodic table, electronegativity is going to increase as you go from the left to the right across a row. So if we look across the second row, for example, you can see that electronegativity dramatically increases as you go across this row. And then from the bottom to the top of a column, it's also going to increase as you go up a group from the very biggest atoms to the smallest atoms. So why do these trends exist? Why is fluorine the best element at attracting electrons to itself? This has to do with the ability to reach the octet state. So again, we said that these guys only have a single electron in their outer shell. And to be able to get to the octet state, it's easiest for these guys to lose an electron to then gain the octet state of the noble gases. You'll notice the noble gases are not shown on this chart. They have very, very, very low electronegativity because they have a full octet of electrons. They don't need any more. So they're not attracted to electrons at all. But when we're down here, these guys find it easier to lose electrons than to gain 7 more to reach the octet state. So these guys have very little attraction for those electrons. So because they have this little attraction, it's easier for them to lose an electron. As you move across and the octet actually gets close to being full, it really increases dramatically the attraction of that element for electrons. So this one is so close to being full, it has very high electronegativity or attraction for that electron. It wants to just pull an extra electron in so that it can reach that stable state of the noble gas electron configuration. So what you see is that fluorine is the smallest and most electronegative atom on the chart. As you go down its grouping, these atoms get bigger and bigger, and the electrons get farther away from the nucleus of the atom. They get farther away from that positively charged center. So electrons, remember, are attracted to the protons that are in the nucleus of the atom. If they're close to the nucleus, like they are in fluorine, because fluorine's a very small atom and it doesn't have very many shells, it's only got 2, the electrons that are in that second shell are tightly bound and held very close to that nucleus of the atom. And so that nucleus is very present in that atom and can attract 1 extra electron very, very strongly. So fluorine is the most electronegative atom on the periodic table, followed by oxygen, and very closely over here, chlorine. So oxygen, you should note, is more abundant than fluorine is, and it's a much more relevant atom when we think of biological systems and when we think about different reactions on the Earth, such as rusting and things like this, all behave because of interactions with oxygen. And so oxygen's really high electronegativity gives it a lot of the properties that we see for the oxygen molecule. So this concept of electronegativity, or the measure of the ability of an atom in a chemical bond to attract electrons to itself, was a concept that was proposed by Linus Pauling. And so you may have heard a lot about Linus Pauling. He actually worked at Oregon State University for quite a long time in his career. And he was one of the only people to receive 2 unshared Nobel Prizes. He had 1 in chemistry, and he had 1 in peace. And so his Nobel Prize in chemistry was for developing this concept of electronegativity and the involvement of this electronegativity concept in both ionic and covalent bonding. And so this was a very important concept in chemistry because it really describes the reasons why different compounds can form, and it gives us a guide rule for trying to make different compounds. Linus Pauling's Peace Prize was because he protested fiercely against the development of the atomic bomb during World War II. And so because of his demonstrations and his active presence in government and in politics at this time, stating why we should not build the atomic bomb and why it should not be used, really led to the Nobel Prize Council to give him the Nobel Peace Prize. Interestingly, later in his career, he was also involved in trying to figure out the structures of both DNA and proteins. And for DNA, he just lost out to Watson and Crick. Watson and Crick actually published after him, actually, but Linus Pauling's structure of DNA was flawed, and so he did not have the correct structure. Watson and Crick actually published the first correct structure of the DNA molecule. So even though you can be really, really good as a scientist, you might not always be right. So this is a very nice periodic table. This guy is also available for printing out on the website. I would print out a copy of this and keep it in your notebook so that you can utilize it in our class activities and so that you can utilize it in the lab activities as well. Because this is going to be a very important chart for figuring out whether things are going to form ionic bonds or covalent bonds. So again, you'll notice that the noble gases over here, they are represented in this chart, but they are not assigned any electronegativity values. They're essentially 0 for the noble gases because they are complete in their octet. So again, the fluorine is going to have the highest electronegativity values, and we're going to see outside of the noble gases, the group 1 elements typically have the lowest electronegativity. You'll see one outlier here, hydrogen. Hydrogen again is going to be in the mid-level for electronegativity, and this is because it's half full. So we can think it only has the s orbital in the first shell, so it could either gain or lose that electron to reach a complete electron configuration. So if it gains one electron, it will look like helium. If it loses that electron, it's just going to have the proton. Because remember, hydrogen only has one electron and one proton. It has no neutrons in its most common isotope. So what we do to try to figure out whether or not a molecule is going to actually accept or donate an electron, or whether it wants to share, is going to be indicated by the electronegativity difference. So in mathematical terms, how do we get differences? We actually have to subtract the numbers. So if we look at our electronegativity chart, if we were going to say that carbon and hydrogen were going to form a bond, their electronegativity difference is going to be 2.5 minus 2.1 is going to be 0.4. So if we look at this value, as a rule of thumb, if the electronegativity differences are less than 0.5, this is going to result in what's called a nonpolar covalent bond. And then differences between 0.5 and 1.7 are going to indicate that there's increasing polar covalent bonds. So the difference between a nonpolar covalent bond and a polar covalent bond, covalent bonds mean they're sharing electrons. Nonpolar means that they're sharing equally. So if they're sharing equally, so like hydrogen and carbon would share electrons equally, each of these atoms would be able to have the electrons for the same amount of time, essentially. They'd be spinning around this one, and then around this one, and then around this one, and then around this one. So if we have a polar bond, it means that the sides of the compound become polarized. They become partially positive or partially negative in their charge state. So if we look at the electronegativity difference between carbon and nitrogen, it is about 0.5, and so you don't have very strong polarity. that associates with carbon and nitrogen. But you have a bigger difference when you have carbon and oxygen coming together. It's a difference of 1 electronegativity unit. And so what this says is, since oxygen is much more electronegative than the carbon is, it has much more attraction for the electrons than the carbon does. And so when it shares electrons with the carbon, in this case, it's going to hog the electrons more of the time. So the electrons are going to be spinning around this oxygen maybe 8 times, and then it'll spin around the carbon. And then it'll come back and it'll spin around the oxygen and again for another 8 times, and then it'll spin around the carbon. So the carbon is not completely positive because it does get to have the electrons some of the time. But it has a partial positive charge, and so when something is partially positive, we give it this delta symbol. So this is the Greek lowercase delta. And so when it's a delta positive, that means it's partially positive on this side of the molecule. And that's because the electrons are being pulled closer to the oxygen more of the time. So on this side of the molecule, we've got this partial negative charge that's associated with the oxygen. So this is a covalent bond. The electrons are being shared here, but they're being shared unequally. The oxygen has the electrons more of the time. So this one is a polar covalent bond. This one we would say is on the edge of being a nonpolar covalent bond. It might have a slight positive charge over here and a slight negative charge over by the nitrogen, because the nitrogen is just a little bit more electronegative than that carbon is. And we can see that again if we're looking at the electronegativity chart. The nitrogen has an electronegativity of 3, the carbon 2.5. So typically, if we assign electronegativity values between 0.5 and 1.7, this is going to indicate that we have a polar covalent situation. If it's less than 0.5, it's a nonpolar covalent bond. And if it's above 1.7, it's going to be an ionic bond. That means that full charges end up forming, that the electrons get fully donated from one atom to the next. So there's no real sharp dividing line between covalent and ionic bonds. It's essentially an energy continuum. And we will do a short video segment that details this in a little bit more detail, because this is a very important concept that you should get across. So ionic bonds then involve full charges. Each atom in the bond either donates or accepts electrons, and covalent bonds involve the sharing of electrons. So you can have 2 types of covalent bonds. You can have a polar covalent bond. This is going to contain partial charges, so the atoms don't share equally. Or you can have a nonpolar covalent bond, and they do not have any partial charges between the atoms, and so they're going to share the electrons equally. So next time we'll talk a little more in depth on ionic bonding.